Okay, so we're going to do our first example of a proof by induction. So here we have this statement. We're saying that if n is some integer, some natural number, and n is greater than or equal to 4, then 2 to the n is greater than or equal to n squared. Now, in order to prove this, we use induction on n. So the base case in this case is that n starts off as 4. So base case, n equals 4. And we should see that in the base case, when n is 4, we have 2 to the 4 is greater than or equal to 4 squared. And this is true because 16 is greater than or equal to 16. And that's the base case. Now, the inductive step, all right, we assume, or we let, I shouldn't say assume, we let 2 to the k be greater than or equal to k squared for k greater than or equal to 4. And what we need to show that the statement is true for k plus 1. We need to show that 2 to the k plus 1 is greater than or equal to k plus 1 squared. Okay, now in order to show this, right, we kind of need to take a little bit of a detour and just do something on the side. So let's just work on the side for a second, and let's just consider what we have based upon the inductive step. So our inductive hypothesis, we say, is this right here. So we have this in our hand, right? So I'm going to write that 2 to the k is greater than or equal to k squared for k greater than, for some k greater than or equal to 4. Now, if I multiply on both sides by 2, right, I'm going to get, and that will keep this equality true, so it's going to be 2 to the k plus 1 must be greater than or equal to 2 times k squared. Right? Because I just multiplied by 2. Again, for k greater than or equal to 4. Now, we should see that if I want to show this inequality, right, this one, that's what I want to show, right? All I need to do is show that 2k squared is greater than or equal to k plus 1 squared. So, we only need to show that 2k squared is greater than or equal to k plus 1 squared for k greater than or equal to 4. And here, I'm just going to go through the sort of like steps here, because we don't know that this is true, but we're going to wind up with this being true. But I kind of reverse this at the end. So I'm going to show it all here on the other side. But let's see what I mean by this. So I don't know if this inequality is true. But if it is true, then I'd have this. Right? Because I just divided by k squared on both sides. And then I'd have, when I FOIL this out, k squared plus 2k plus 1 over k squared. And then I split it up by terms, and I would say 1 plus 2 over k plus 1 over k squared, right? And then I could minus 1 on both sides, and I would say 1 is greater than 2k plus 1 over k squared. And we remember for k greater than or equal to 4. And here is where it is that I can kind of figure out how I want to reverse to get to this one, right? So how do I figure out that I want to reverse this one? Let's see what we have here. We have 2k, right? Let's look at 2k. For k greater than or equal to 4, we must have, right, clearly, we must have 2k is less than or equal to 1/2. right? So that's this piece. And then this piece, right, is that, this is less than a fourth, less than a half, whatever. But, okay, this piece, right, 1 over k squared must be less than or equal to 1/16 or 1/4. It doesn't even matter. 1/4, let's just say. It's technically 1/16, again, for k greater than or equal to 4. Sorry. Greater than or equal to 4. Okay, and these two inequalities should be obvious. And that's sort of where I want to start up at, because then what I can say is I can reverse this whole process and see that the original inequality must be true, right? So if this is less than a fourth and then this is less than a half, then the sum is less than 1. So then this one must be true. And then if I add 1 on both sides, then this inequality is true. And then if I just, refactor this into this, then I have this step. And then in this one, I refactor again. And then in this one, I multiply by k squared, and I have this inequality. And then once I have this inequality, then this one must be true. And I just did the work here, and now I'm going to make the argument forward on this side. So we're going to just start off and we're going to say something basic. We're going to say 2 over k, or we're going to say 1/2 is greater than or equal to k, 2 over k, right? And I'm looking over here to see for k greater than or equal to 4, right? And, right, 1/4 is greater than 1 over k squared for k greater than or equal to 4. So these two together imply that 3/4 is greater than or equal to 2 over k plus 1 over k squared, right? Because if I add these inequalities, then I get this resulting inequality. And this one for sure implies, and we don't need to worry about it, 1 is greater than or equal to 2k plus 1 over k squared. And then when you add 1 on both sides, you get 2 is greater than or equal to 1 plus 2 over k plus 1 over k squared. And then when you multiply by k squared on both sides, you get 2k squared is greater than or equal to k squared plus 2k plus 1. And then this refactored is k plus 1 squared. So we got 2k squared is greater than or equal to k plus 1, again, for, this is key, for k greater than or equal to 4. So this, right, with the inductive step, right, and we know we have this step, right, we know this is true, and then this one, right, so I have, again, just going up here, right, this with, right, we started off with 2k is greater than or equal to k squared for k greater than or equal to 4. I multiply by 2 on both sides, right, and I get this. But now I showed that 2k squared is greater than or equal to k plus 1 squared. So then this, I could just put that right here and just say k plus 1 squared. And then this chain of inequalities shows this, which is what I needed to show. 2k plus 1 is greater than or equal to k plus 1 squared. And I've shown the base case and the inductive step, and we're done.